Hey, welcome to another video. I hope that you are ready to start wrapping up this stuff about population modeling because we only have about 3 more videos, this one and 2 more, and then we're going to move on to acceleration and some oscillation type problems. So in order to wrap this up, we're going to talk about how you know when something is going to go to a number as far as a population or explode. And so we're going to talk about something called equilibrium solutions. We'll talk about critical points, we'll talk about stability, funnels, spouts, and then we'll move on and talk about harvesting and stocking populations in another video. So today's video, I really want to get the point across to as to how you would know when our population is going to explode or go to a number when you're not based on something like the logistic equation or an extinction model, when we can't immediately see that. And so we're going to discuss that in this video today. So let's get right to it. Let's look at a differential equation like the derivative of x with respect to time is x minus 4. Now, here's the premise to this question. What if your initial, let's say this is a population of x, so maybe x is our population with respect to time. What if your initial population or your initial x value was 4? Well, what would that do? Because if you plug in a 4 right there, 4 minus 4 is 0. Wait a second. If 4 minus 4 is 0, that means that the way your x changes with respect to time would be 0. There would be 0 change. That's the way that our population would be changed with respect to time wouldn't change. Our population of x, or whatever x is, would not be changing. In general, if our derivative with respect to time is 0, then obviously nothing would change here. The rate of change is 0. Nothing's changing. When that happens, so when you have this value, this point, like 4 in this case, or whatever is making your derivative 0, just like in Calculus 1, we call that a critical point. Did you remember that? When you took a first derivative and you set it equal to 0 and you said, oh, where the slope changes from positive to negative, we have this horizontal tangent, and you go, the slope is 0. When the first derivative is equal to 0, we have what's called a critical point. And lots of important things happen at critical points. Same thing here. If we have a model, the way that something's changing with respect to time, and if this equals 0 at any point, we gain what's called a critical point. We have a critical point here. So specifically, x equals 4 is called a critical point. Oftentimes, we'll also hear it called an equilibrium solution. And why that is, if you have an initial value of 4, so x sub 0 equals 4, and you plug that in here, you can't possibly get a change from your population, if we're going to call this a population, or your x function, if you want to call it that. There will be no change. It will stay the same forever and ever and ever and ever. So if we start exactly at 4, there's going to hold this equilibrium. Nothing will change from that. You can't gain, you can't lose. It's going to be at a no change, a zero-sum sort of an equation. So one time, just to recap this one, with our differential equations, I'm trying to teach you when we will stay at the same level, when we will explode, when we will go to a carrying capacity, or vice versa, become extinct or come to a limiting population, or when we're going to stay the same. I'm going to talk about that. To start there, anytime your derivative is 0, you have what's called a critical point. We know that from Calculus 1. Here, what that's going to mean is that if you start at that critical point exactly, then you would have a change in your population, whatever your function is, of 0. Your rate of change is 0. It cannot change. That solution of the critical point is oftentimes called an equilibrium solution because you are at equilibrium. Nothing's gaining, nothing's losing. So an equilibrium solution. So how do we find them? Just like in Calculus 1, it's a very simple idea. Because your dx dt is a derivative, that's fantastic. This is a derivative. So if our dx dt, our derivative of x with respect to time, is some function of x, which that's what we have here. If that's some function of x, then where your derivative equals 0, man, see this. Where your derivative, this is the derivative, where your derivative equals 0, it's going to give you these critical points. So running through this, if you want to find critical points, all you got to do is set your function equal to 0 because that function is the derivative here, and critical points are found by setting your first derivative equal to 0. So we're going to set our first derivative, our function of x, which is our differential equation. We're going to set it equal to 0. That's going to give us critical points. So let's consider a critical point like x equals c, a critical point. We kind of went through it, but if x sub 0, if your initial x is the critical point itself, we call that an equilibrium solution. Nothing's going to change. Our derivative would be 0. You can't gain, you can't lose. We are horizontal right there. So this would be an equilibrium solution. Yeah, I suppose that's not all that exciting. I mean, it kind of makes sense, right? So if you get a derivative of x with respect to time, and you know that's your derivative, your first derivative of some function, and you say, hey, I plug in some number that's going to make it 0. Obviously, we're not changing from that. That's not a hugely surprising thing. We're going to stay at the same level forever because the derivative of 0 says we can't increase, we can't decrease, our population stays the same, or whatever your function of x is stays the same forever. The interesting things happen when your initial condition is above or below that critical point. So let's talk about what would happen if our initial condition is greater than c or less than c. Some interesting things are going to happen. So wait a second. If our initial condition is greater than c, then really only two things could possibly happen. Now, I'm not talking specifically about this one differential equation, but in general, here's what could happen. If we start, here's our critical point. If we start above that, then only two things could happen. Either we explode forever or we shrink to c. If we start below that c, we either gain to c or we become extinct or go to some lower critical point. So we're either getting to or away from that critical point. That should kind of make sense. There's only two ways to go. If you've got a critical point and you start at it, you're not going to change because your derivative would be 0. It's an equilibrium solution. If you start above it, we will either explode or we will shrink to c. If you start below it, you're either going to gain to c or you're going to fall or go away from c if you want to, kind of spout out of that or drop to a lower critical point or go extinct. So if we have an initial condition greater than c, we will either explode or shrink to that c. What if it's less than c? Well, we can either gain to c or we can become extinct. If this is the only critical point, these are the only outcomes. So just to make sure we got that. Derivatives mean rate of change, obviously. So if we set our first derivative equal to 0, we have what are called critical points, and if we have an initial condition that is that critical point, nothing's going to change. Slope would be 0, function can't change, you have an equilibrium solution. The interesting thing happens when our initial condition is above or below that critical point. If we're above, we're either going to become extinct or shrink to that critical point. If we're below, we're either going to gain that critical point or become extinct. Question is, which one's which? And what's beautiful about this, because it's a first derivative, because it represents the rate of change, we can do the first derivative test or a sign analysis test or just look what the slope is doing and it will tell us exactly what's happening around those critical points. So if our first derivative is this function that we're talking about, so this is a derivative. I know it looks a little different than the first derivative test from calculus 1 because there's no prime, but keep in mind, this is the first derivative of some function x. What we're going to do is we're going to simply put our critical points on a number line and do sort of a modified sign analysis test. So we'll look at this and just plug in a number, plug in something greater than c, and see what your function is doing, see what your first derivative is doing. And there's really 4 cases. So sign analysis test, first derivative test, whatever it is, there's really only 4 cases. If we plug in a number greater than c and we get a negative, and we plug in a number less than c to our first derivative right here, and we get a positive, what's happening is that our function would be decreasing if we have an initial condition greater than c. It will be decreasing. But if we have an initial condition less than c, our function would be increasing. Right there we have what is called a stable critical point. What that means is that around that critical point, in the neighborhood around that you would have numbers, whether you're less than or greater than, you're going to ultimately go to that critical point. That's called stability, or that's a stable critical point. So if we start above it, it's going to drop to it. If we start below it, it's going to gain to it. This is what we call stable. And how would it look? I'm going to draw that right here. How would stable look? If we have an initial condition less than our critical point, so down here somewhere, this says that we would be gaining. So we'd say, okay, so you're testing this, you're looking at first derivative, you found your critical points, you have them on some sort of a sign analysis or a number line, plug in a number less than that, and you get a positive. Plug in a number less than that, and you get a positive. Wait a minute, positive slope. The function is increasing. We would get something that looks like this. Well, wait a minute, if you plug in something higher, you have a negative. Negative means negative slope, means your function is decreasing. We would get something that looks like this. So it's kind of messy. But we have this kind of convergence of both of our sides here. So we have a stable critical point if we have both, whether we're positive or negative, above or below that critical point, we end up getting to it like an asymptote. Right there, what you call that is a funnel. So everything's funneling to that number of c. That's what stable means. That's what the picture would look like. So what are the other options? Well, what if you had this critical point and you plug in a number greater than that and you get a positive? So that means that, let's see, if we plug in a number greater than our critical point, we got a positive. That means increasing. So positive slope means increasing. That would be a function going away from that critical point, gaining away from it. Remember, you're above it and you're increasing. Or what if we plugged in a number less than our critical point to our first derivative and we got a negative? Well, that would be decreasing. That's away from that critical point. That situation right there is called unstable. An unstable critical point is where your function tends to go away from that number. It's like it's fleeing the scene, all right? This is like gravity. This is like, stable means I'm gonna go right to it no matter what. Unstable means I'm gonna go away from it no matter what. And you can see it right here. If you got some number that's starting above your c and you find out that the first derivative is positive, that means that you are increasing. Now you're going to gain away from that number. You're going to get something that looks like this. Or below. So if we have something that's negative, we plug in a number less than our critical point in our first derivative, we get something negative. Then for every initial condition less than that critical point, we would have a negative slope. Negative slope means function is decreasing. So I'm starting here and it's decreasing. That's going to look like this. That is what we call an unstable critical point. And a lot of people refer to that as a spout. So a spout says, I'm going away from it. Kind of going out from. Funnel means going into, spout means going out from this particular critical point. I hope this is making sense. I hope that you're seeing the relationship. I hope I made it very clear that what an equilibrium solution really means is that your slope's not changing. If your slope is zero, that means your function can't change. If your slope is positive, your function's increasing. If your slope is negative, your function is decreasing. And then compared to our critical point, how that interacts, how your slope interacts around your critical point will tell you whether you have what's called a stable critical point or a funnel, or unstable critical point, or a spout, going to or going away from that critical point in a neighborhood around it. The other two conditions are called semi-stable. Now let's take a look at it for a second. What if you plug in a number greater than your C and you get a plus, and you plug in a number less than your C and you get a plus? Well, wait a minute, what's that mean? Slope would be positive, so we would be increasing. Slope would be positive, so we would be increasing. That seems really weird. This is called a semi-stable critical point, because if we start below our C, initial condition below C, we're going to have a positive slope. We will be increasing. We're going to get to that C eventually, so we're going to look like this. So it looks something like that. But if we're above that C, we're going to be also increasing. So it's kind of a half funnel for those values below and a half spout for those values above. This would be increasing still. So we start above C, we have a positive slope, that'd be increasing still. We get something that looks like this. And so we have this below C, you get to it. Above C, you leave it. That's called semi-stable. Likewise, what if you plugged in a value above C and below C and got negative? That means that we'd have a negative slope. That means our function would be decreasing in both of these cases. Well, it's still semi-stable, but it'd look a little bit different. For those values above C, you'd have a negative slope. The function would decrease, but it would decrease until you get to C. So it's going to look like this. That middle one's a little funky, sorry. So it's going to decrease until you get there. But if you have something below C, some initial condition below that critical point, you're still decreasing. The function's still dropping. So you'd have this same sort of idea where you have a sort of both a funnel and spout, the same idea. For those values, initial conditions starting above C, you'd be dropping to it. For those below C, you'd be going to extinction. Now, I do want to say one thing about this. This is for only one critical point. So in the future, when we have 1 or 2 or 3 critical points, which we're going to see at some points, you could have another critical point up here, in which case this would gain and then get to it. So around this one critical point, we talk about whether we're leaving it or getting to it. That's sort of the idea here. So I'm only showing you one critical point, but keep in mind, if I've got another one, I could leave from one critical point and drop to another. That's perfectly acceptable. But it is my lowest critical point. If I leave it, if I'm below it and I leave it, if I spout out of it, I'd be going to extinction. If I have my highest critical point and I leave it, I'm going to be going to explosion. I hope that makes sense. I hope I've made it very clear the interplay between critical points and this funnel, spout, this stable, unstable, and semi-stable cases. These are both called semi-stable. What I'm going to do now is I'm going to come back up here and we're just going to walk through this. I'm going to leave this on the board. We're going to see what case this actually is. So what we've talked about so far is that a first derivative is a slope. When you set a first derivative equal to 0, you get critical points. And now we're using this in terms of our population or our modeling situations to say, what's the graph going to do around there? If that's a differential equation, what would the function look like? Well, it would depend on our initial condition. And that's exactly what we're saying. If our initial condition is 4, we have just this equilibrium solution. If our initial condition is above my critical point, I'm going to be in one of several cases. I'm either going to drop to it or leave it or drop to it, depending on what my first derivative is actually doing. Same thing for our initial conditions less than C. So we're looking at this, we're saying it is a first derivative, but since I don't know my parent function, I'm kind of guessing at what it's going to look like, and it's based on our initial condition, what it's actually going to do. Hope this makes sense. I'm going to come back up here and we'll show you what this does. Okay, so here we go. Number 1, we'd say this right here is a differential equation. It means a first derivative. So if x minus 4 equals 0, then that's going to say our slope is 0. That's called a critical point. So we're going to say that x equals 4 is our critical point. What we do after that is we do what's called a sign analysis test, or you can hear a phase diagram or a first derivative test, all the same thing. We're going to say our function, our f of x, which is x minus 4 right now, is creating for us some sort of a phase diagram based on a critical point of 4. So we just take our 4, you put on a number line. And then we're going to plug in, just like every first derivative test ever, a number greater than 4 and a number less than 4, and see what our sign is. I've given you a very simple case. We'll deal with some much more advanced cases in the next video. But let's plug in a number like 5. If I plug in 5 to my first derivative, remember our function is x minus 4, I'm going to get a positive. Now, I don't care that it's going to be 1. I care that it's positive. So this would be a positive slope. It says that we are increasing. Now get this. The slope is positive. Slope is not increasing. The slope is linear. You can see that. The slope is just linear, x minus 4. Here's what this says. It says that because the slope is positive, if I give it an initial condition greater than 4, my slope will be positive. That family of curves would be a family of curves where all the slopes would be positive. That means that the family of curves, all of them would be an increasing function. Again, because this represents the slope, I'm finding critical points. If I plug in a number greater than that 4, that initial condition is more than 4, it's going to create for me positive slopes on or give me a family of curves that all has positive slopes. And this is coming from a family of curves with positive slopes. Positive slopes means a family of curves, each one of which would be increasing, just like this. So 5 is more than 4, 5 is more than a critical point. We are getting a family of curves with positive slopes on that condition, all of which would be increasing. Now plug in something like 3 or 0, that'd be fine too. 3 minus 4 is negative 1. I don't care about the 1 so much, I care that it's negative. So think about that. If I give myself an initial condition of 3 or something less than my critical point, like 3, 2, 1, 0, whatever, that means that I'm getting a family of curves here, all of whom would have negative slopes. That would be all decreasing. All of these will be tracking away from that 4. Think in your head, is that stable or unstable? We're going away from it. It's spouting water. It's going to get away from me. This would be unstable. In fact, it's going to look like this. That's exactly what we just said here. You have a critical point, C. It's going to look like this. At x equals 4, if we start above it, we are exploding. If we start below it, we are extincting. If we start at it, we stay the same. There's no other critical point, so get this. Like, this is the only critical point, right? It's the only place where our slope could equal 0. That's it. So if we start above that, we are going to get a population explosion, if this model is population, or a function explosion. If we start below that, we're going to get a population extinction or a function extinction. It's going to go to 0. This has to make sense right now. I hope you've seen it. Are you seeing the stability versus instability or instability of this? We're using first derivative, using the idea of slope. We're saying positive means increasing, negative means decreasing, and showing where that is in relation to our critical point to determine whether we have a spout or a funnel, stable versus unstable. Now, can we go a little bit further and actually solve the differential equation? Well, of course we can, and we're going to see why this is the way it is based on our differential equation. So because we have a separable equation here, and we get our x's dx's, and our constants dt, and take this integral, and exponent on both sides. We've done this so many times. I'm going kind of quick here. And this whole thing is c. And if we replace that with c, replace that with t. Do you remember this? Hope you remember. As soon as you get that arbitrary constant, especially when you have ln's, now we're going to plug in an initial condition. You go, what do you mean an initial condition? Well, let's just say that at x of 0, you have some sort of an initial condition. Just use that. Use the x sub 0. So that x sub 0 is happening at time 0. Okay, so e to the 0 power is 1. This c would equal x sub 0 minus 4. And if we plug that in, so we have this x minus 4 equals x sub 0 minus 4 e to the t. And just add our 4. And take a look at what this would do. Depending on what our initial, I hope I didn't go too fast, by the way. This is just a separable differential equation. We're saying our initial condition is x sub 0. So when we solve for our c, we have x sub 0 when t is 0, then c is x sub 0 minus 4. We've taken this, plugged it in right there. It's right there, and we've just added 4. But look at what happens. Look how this is a vertical shift of 4. That means everything happens around that 4. This right here is this number. So it's shifted up 4 units from x equals, so from y equals 0. So x equals 0. From 4 units up. Now, take a look at this right here. Look what would happen. If x sub 0 is more than 4, you have a positive number. A positive number times the exponential. Man, e to the t, it's the same exponential, you know. So if this is more than 4, you have a positive exponential. It's going to grow. That's exactly what that says. It says you start at 4 and then add a function to it that is growing. That is this. Now, what if this is less than 4? If this number, your initial condition, is less than 4, then something less minus 4 would be something less than 4 minus 4 would be negative. So you'd start at 4 and say you'd subtract, oh my gosh, wait a minute, negative e to the t, that would look like this because it's a reflection across the y equals 0 line, so x-axis. So if this is negative, remember, negative e to the t, some sort of negative e to the t, it's not a dropping like this, it's a reflection of your exponential. So instead of climbing, you'd reflect it, you'd be dropping. That's what these say. If your initial condition is less than 4, you have a negative exponential. So go up to 4 and then do a negative exponential. That's why this looks the way that it does. This is just a really nice way to see it. So like when we go through our next set of examples in the next video, what's going to happen is I'm going to do a lot of them just by finding my critical points and making these graphs. It's very nice. For a few of them, we're going to go all the way down and solve our differential equation and say, do you see why this is? Do you see that that 4 is this critical point? Do you see that depending on what your initial condition is, we get a positive exponential? If it's above 4, a positive exponential. If it's below 4, a negative exponential. It's going to spout away from that. That's an unstable critical point. This right now should be making a lot of sense to you. I hope I've explained it well enough. Obviously, I think it's really cool. So it's very interesting to me that this stuff works and that you do your differential equation and models exactly what we saw with our first derivative test. So we're going to come back. We're going to do one more example all the way through. I'll explain the same things and then we'll be done. All right, so one more. We're going to work our way through it. I'm going to try not to go too fast to make sure that we really, really understand this. But next time we're going to do a lot of examples too. So right now I just need the overview of what's going to happen to be there. We're going to get stability or instability, an unstable critical point for each of these cases. Sometimes we can get semi-stable. We'll see that in the next video, how that looks. But what needs to be there right now is how the first derivative, differential equation is a first derivative, first order differential equation, how that relates to increasing and decreasing depending on your initial condition. That is what is key, is that you understand that because we don't have the actual function x, we have the derivative of that function, that when we go back to it, we're getting a family of curves. And that family of curves is dependent on what our initial condition actually is. That arbitrary constant, it's not so arbitrary if you have an initial condition, is it? Because you solve for that and it says, oh, this is giving me a specific curve. And where that specific curve is and how it behaves depends on that initial condition of x. That's a big deal. And we're seeing that in the course of our graphing here. We're seeing how that initial condition drastically changes what happens. So let's go through it. We're noticing we got a first derivative, differential equation with respect to time, and we have x, 3 minus x. And we say, well, wait a minute. So if we've got 3 minus x, and that's equal to the first derivative of our function, then this itself, that's a derivative. And so we say we can find critical points all the time by setting our derivative equal to 0 and solving. So we have a critical point very easily of x equals 3. Now get this. Not always, if you're above the critical point, do you gain. You can't say that. And so I wanted to make that clear when I first introduced this concept in the first 10, 15 minutes, but I really can't do it by looking at x minus 4, because if we were above that, we were gaining, below that, we were decreasing, and you saw that on the first derivative. But in general, you can't make that statement. You can't say, every time I'm above a critical point, I'm gaining. That's not true. Because if I plug in a number like 4, I'm going to get a negative slope. I'm decreasing. That's why I said at the beginning that where our critical point is, if you start above it, you can either increase or shrink to that critical point. If you start below it, you can either increase to it or go away from that critical point. It all depends on how your first derivative behaves. That's why we have to do the sign analysis test. We can't just arbitrarily say, oh, you're above it, you're going to climb forever. That's not true. Right now, we're sort of putting together the logistic with the explosion extinction ideas in a more general term here. So when we look at this, we go, yeah, our critical point's 3. Let's go ahead, take the time, and do a first derivative test. So our function is 3 minus x. We've got a critical point of 3. All that needs to happen right now, since we do not have our function itself, we just need to understand what our slope of our function is doing. This is the slope of our function. So if we start with a value greater than 3, like 4, 3 minus 4, so our function here is 3 minus x. If we start with 4, we're going to get negative 1. We are understanding that for every value above 3, without exception, there's only one critical point. There's only one possible point where the sign of our function can change. It's 3. Every value above that 3 is going to have a negative slope. Every single value, initial condition above that, is going to give you a family of curves with negative slopes. Every curve will have a negative slope. Every curve will be decreasing. Get that? I'm going to say it again. It's so important that there's only one critical point here. There's only one number where our slope is going to change signs, and that number is 3. Every single initial condition greater than 3 is going to give you a curve. Remember, this is a slope of a curve. Every initial condition greater than 3 is going to give you a curve that has a negative slope. That means every single initial condition greater than 3 is going to give you a curve that is decreasing. These are all going to be decreasing. Now, do the same thing with a number less than your critical point, like 2 or 1 or 0. It doesn't really matter. Plug in 2. 3 minus 2 is positive 1. So this is your slope, all right? This is your slope. It's not your function. It's telling you that your initial condition is the function you get is dependent on your initial condition. So if I plug in a number less than 3, if I have an initial condition less than 3, what that's saying is that that whole family of curves, every single initial condition less than 3 is going to give me a function whose slope, this is slope, is positive, whose function is increasing. That right there is giving us what's called a stable critical point. It is going to look just like this. This is how this is going to look. We're going to have some sort of a graph where the family of curves depends on what your initial condition is. If we have an initial condition that's greater than 3, we are going to get functions that are decreasing. If we have initial conditions less than this, we're going to get functions that are increasing. We're going to get what's called a funnel. Things, no matter where we start, we're going to funnel into something near that one number as time goes on. Do you see it? Am I explaining well enough the interplay between the first derivative test, what critical points are from, like, I don't know how many semesters ago that was, into what your family of curves has to be doing. And the fact that it's based on your initial condition, that's huge, because in Calc 1, you sort of go backwards, don't you? You have a function and you take a derivative and then you say, oh, the function is doing this. Well, here we're saying I have the derivative of the function. What could the function be doing? Oh, well, that's a different question. What that means is that I'm doing my first derivative test, but I'm using it to model my function, not the other way around. Not to kind of gain my function, not saying this is how the function looks, but this is all the possible functions we would ever get. And more than that, it depends on where I start. So if I'm starting above, in this particular case, I'm getting a family of curves that is all decreasing for every initial condition greater than 3. For every initial condition less than 3, I'm getting a family of curves, all of whom are increasing. And when we put that together, we have this funnel idea. Let's see how that plays out when we actually do our solving of our differential equation. So you've seen me do a few different techniques and give you a lot of different options over the last 2-3 videos on how you structure these. I've done things like factored out negatives when appropriate. I've left them in there. I've tried to give you a variety of ways to do it. That way, at least one of them will stick. In this case, I'm pulling out that negative, and the reason why we do that, it's not super important, I think I've mentioned that many times, is because when you start taking integrals, I don't want you to take an integral of this and accidentally give me this. Oops. Because that's a problem. You need a u sub and you'd get a negative. So the reason why you'll see me do things like factor out a negative when it doesn't appear like I actually need to is just for that reason. So in our case, we have this ln absolute value x minus 3. We've got negative t plus c sub 1. We have an ln. We're going to wait to plug in our initial condition until we take that both sides as an exponent on e. We have x minus 3 equals this plus or minus e to the c sub 1 times e to the negative t. We've done this many, many times. This right here is our constant. But we also know that constants are always, our arbitrary constants are always found by an initial condition. So what is our initial condition? Well, we don't have a specific one. Remember what we're doing. We're trying to be general. We're trying to show the picture of our curves depending on our initial condition. So when you get done with this, you should be able to plug in any number and say, hey, for numbers greater than this number, I'm going to explode or shrink to. For numbers less than number, I'm going to, well, maybe become extinct or gain to, whatever that number is. So we're going to use this initial condition to create a model of our general solution here, whatever our initial condition happens to be. Let's plug it in. When I plug in t equals 0, I get x sub 0. That gives us 1, so our c is x sub 0 minus 3. Now when we substitute that back in right here, that's an x minus 3 equals x sub 0 minus 3 e to the negative t. I'm going to take just a side step for a moment. And I'm going to tell you on some of the harder examples that we're going to cover, sometimes I will solve for c right now. I'll hold this off to the side, but I'll leave the c in here and I'll solve this for x and then I'll plug the c back in. Because doing this on much more advanced examples can get really, really, really messy. And so you'll see me go, okay, plug in your initial condition now, leave your c, just remember what that is, solve for x, and then plug in your c later. Otherwise, especially with fractions, it gets pretty crazy. So I'm going to show you some of those techniques in the next video as well. Man, we're almost done. We're quite there. So we have noticed that's a slope. This is the slope of every single function of x, that whole family of curves. And we have determined that what that slope is, the sign of that slope depends on a critical point. Where the slope equals 0 is where your signs could change. Things above 0 are positive, below 0 are negative. So that critical point is critical. It tells us where our slope is positive and therefore increasing, or negative and therefore decreasing. And so what we've determined, because that's slope, because that represents the slopes of the general solution or every family of curves that would have this as a slope, we're saying that everything above that value of 3 is going to give us a family of curves that is decreasing. Every initial condition less than 3 is going to give us a family of curves who are increasing. So we have a picture like this. Now let's make sure that what we've solved on our differential equation actually models this. So we had the slope of the function right here, guys. This is the function. This is every possible function that would have this as a slope. This is your general solution, and it's based on whatever your initial condition is. Now let's look. That 3, hey, that's a vertical shift. That says that I'm going to have some important stuff happening at that horizontal asymptote, that equilibrium solution of x equals 3. That's important. If my initial condition is 3, I get a horizontal line. Now, what if my initial condition is more than 3? More than 3. Well, something more than 3 minus 3 would be positive, but this is an exponential with a negative exponent. That looks like this. Those are droppies. Remember that? E to the negative t looks like that. Wait a minute, that's what this looks like. So if I have an initial condition greater than 3, I will get positive decaying exponential, just like it shows. If I have something less than 3, I would get, let's see, again, something less than 3 minus 3. That would be a negative decaying exponential. So a decaying exponential flipped over. So wait a minute. If I take a negative, so remember, this is negative. Negatives reflect about the x-axis. It would look like this. This would be e to the negative t, negative e to the negative t. E to the negative t is a decaying exponential. Negative e to the negative t almost looks like a logarithm here, but it's not, but it's a reflected decaying exponential. It says that you're taking this and flipping it over. That's all it says. It says that you are going to be looking just like this for every value starting less than 3. That's what this means. This would be a stable critical point. This is called a funnel. It's exactly what we get right here, which I prefaced. The last two I'm going to do in another video. So when we get there, right now I really would encourage you to go back through and try these two on your own. They take maybe 5 minutes once you understand it. I mean, it's not that hard. My job today was to explain to you how the interplay, how this is slope and therefore represents a slope of some parent function, some general equation, some general solution, and to show you that depending on your initial condition, you're going to get a different type of curve. Something increases or decreases depending on what your initial condition is. So I hope I've done a good job of that. I hope I've explained, and you should understand what, man, it sounded like a lot when I first introduced it. You should understand now what an equilibrium solution is. Something that makes your slope 0. It's also called a critical point. You should understand that depending on whether we are greater than or less than that critical point determines whether we have an unstable leaving or stable coming to that critical point, or both, leaving and coming to, or coming to and leaving. Stable, unstable, and semi-stable cases. So we've talked about equilibrium solutions, we've talked about stable versus unstable, we've talked about funnels and spouts, and I hope that I've shown you the interplay on how the differential equations actually show that. But could you imagine not actually doing this, getting all the way down? Wouldn't it be hard for you to see that, it would be hard for me, to see that this looks exactly like that without this first? So this is really important. Your first derivative test is huge. It shows you what's actually going on around those critical points. Then your differential equation says, oh yeah, now that I know what that picture is, I'm able to kind of see it. So I hope that makes sense, because this is what we're going to do for like the last 3 examples in the next video. I'm just going to show you the pictures of them because we'll have a very good interpretation of what's going on. So I will see you for the next video when we talk about a few more examples and kind of refresh your memory on stability and instability, being stable and unstable, spouts, funnels, and we'll talk about semi-stable. Have a great day. I'll see you for that.